Let's explore the triple alpha process that powers red giant stars and discover which intermediate nucleus forms first. Red giant stars are massive stellar objects where incredible nuclear fusion processes occur in their cores. First, let's understand what the triple alpha process actually is. The triple alpha process is a nuclear fusion reaction that converts 3 helium nuclei into 1 carbon nucleus. This process occurs in red giant stars at extremely high temperatures of around 100 million Kelvin. The overall reaction takes 3 helium-4 nuclei and produces 1 carbon-12 nucleus plus energy. Here we see 3 helium nuclei combining through multiple steps to eventually form a carbon nucleus. Now let's identify the crucial first intermediate nucleus that forms. The process begins when 2 helium-4 nuclei collide and fuse together to form beryllium-8. This is the first step. Helium-4 plus helium-4 produces beryllium-8. Each helium-4 nucleus contains 2 protons and 2 neutrons. When they fuse, they create beryllium-8 with 4 protons and 4 neutrons. The key question is, why is beryllium-8 so incredibly unstable? Beryllium-8 is one of the most unstable nuclei in existence, with an extremely short half-life. Its half-life is approximately 2.6 times 10 to the negative 16 seconds. That's less than a trillionth of a second. The beryllium-8 nucleus is so unstable that it immediately wants to break apart in all directions. Let's understand the nuclear physics that makes beryllium-8 so unstable. The reason for this instability is that beryllium-8 has a positive Q value for decay, meaning it releases energy when splitting. When beryllium-8 splits back into 2 helium-4 nuclei, it releases 0.092 million electron volts of energy. The system has lower energy when it exists as 2 separate helium nuclei rather than 1 beryllium-8 nucleus. This energy diagram shows that beryllium-8 sits at a higher energy state, while 2 separate helium nuclei are at lower energy, making the split energetically favorable. If beryllium-8 is so unstable, how does carbon ever form in this process? The answer lies in the extreme conditions inside red giant cores with incredibly high density and temperature. In these extreme conditions, before the beryllium-8 can decay, a third helium-4 nucleus can collide with it. When this happens, beryllium-8 plus helium-4 produces stable carbon-12 and releases a gamma ray. The collision must happen within that incredibly short window before beryllium-8 decays, creating stable carbon-12. There's actually a special quantum state that makes this process possible. Physicist Fred Hoyle predicted a special energy level in carbon-12 that makes this reaction much more likely. This resonance state increases the reaction rate by many orders of magnitude, allowing carbon formation despite beryllium-8's instability. The Hoyle state resonance occurs at 7.656 million electron volts above carbon-12's ground state. This diagram shows the Hoyle state energy level where the resonance occurs, dramatically enhancing the probability of carbon formation. Let's summarize what we've learned about the triple alpha process. Beryllium-8 is the crucial first intermediate nucleus that forms when 2 helium-4 nuclei fuse. It is incredibly unstable with a half-life of 10 to the negative 16 seconds because splitting back into helium releases energy. The extreme density and temperature in red giant cores allow a third helium nucleus to react with beryllium-8 before it decays. The Hoyle state resonance dramatically increases the reaction probability, making carbon formation and ultimately life itself possible. The triple alpha process remains one of the most fascinating and important nuclear reactions in stellar physics, responsible for creating the carbon that makes life possible.